Welcome to the 6th lecture in the course on statistical mechanics of phases and phase transitions. In this lecture we will continue chapter 3. We will look at broken symmetries which we have seen in the last chapter, in the last lecture, and we will also look at some response functions. So let us start with some review. So we have seen that broken symmetry is a very useful concept in characterizing phases. We have seen that there is a concept called as an order parameter which will pick up a non-zero value in a broken symmetry phase. So it can be used to diagnose broken symmetry. To model broken symmetry and or spontaneous symmetry breaking in theory, we have to first add a symmetry breaking field, take the thermodynamic limit, and then set the symmetry breaking field to 0. So this is what we saw in the last lecture. In this lecture we will just finish up a few things that we did not discuss last time, namely the formulation when you have fields in a continuum rather than degrees of freedom on a lattice. We will also discuss a bit about ground state and excitations of systems, and finally we will polish off with a theory of responses to stimuli. So this is what you can expect in this lecture. So first we will start with fields in continuum arenas. So these are degrees of freedom which live in the continuum. So these are typically, for every point in the continuum space, namely point in X, there is a field. We can think of this as an n component real valued field. And remember that these components are not components related to the spatial coordinate basis, but they are components related to some internal degree of freedom, and there is an internal basis, and these components are related to that basis. And what we would like to do is we would like to construct a model that has all the symmetries of the arena as well as the ON internal symmetry. So now that we have got the degrees of freedom, how do we write a Hamiltonian in the continuum for this? Okay. So the important point you want to note here is that the Hamiltonian will be a functional of the field phi. What does that mean? So the field will be a function defined over space, so every point has a value of the field, and for a given function you have to give me an energy of the configuration. So what I have, the energy is now a map from the space of functions to real numbers. So this is one such functional I have written down here. So this has several terms. There is a term where the gradient of the field is dotted with the gradient of the field itself. So now you see this mu is a space index. It is the index that looks at the d different coordinate directions, and it takes derivative in the muth coordinate direction. So remember, this has to be a scalar. So what happens is this mu index is contracted with this mu index, and we have used repeated index summation convention. And so basically what I have is I have contracted the space index, and I have also contracted the internal index or the internal component index, the alpha. So I have a term such as this, and I have a term which does not depend on the gradient, and then I can just think of this as some kind of power series in this, and you can see that I have a term which is quadratic in phi and quartic in phi and so on. This is the term quadratic in phi. So I can also write this in a nice compact way, which is what we will be doing in future. We can think of this as gradient phi square. By square we mean that it is a short form for writing out this full thing, and phi square is again a short form for this, and phi to the 4 is a short form for this. So this energy functional now has a set of parameters k, t and mu, and they are the intrinsic parameters. In the way we have set it up, they will not immediately get dimensions of energy. We will revisit this problem later in the course, and we will see what are the dimensions of these and why those dimensions are important and so on. Okay. So it is a nice exercise for you to now to pause the video and work out the details of showing that this functional has all the symmetries that we talk about. Namely, it has all the arena symmetries as well as the internal ON symmetry. Okay. Now comes the next important step, which is computing the partition function. There is an important technical device that we have to use in computing partition functions of fields. When I have a lattice, then the degrees of freedoms are sitting on the lattice sides, then computing the partition function is somewhat transparent in the sense that it is conceptually very easy. There are, if I have n sides, there are n degrees of freedom, and I just sum over all possible configurations of these n degrees of freedom. Here I have to sum over the all possible field configurations. So in this sense, the integral that I am doing is over the space of functions. So these are called as functional integrals. I will not get into the mathematical details of functional integrals right now. Later in the course, we will see how to think about them in some, at least in some physical way, where we have some understanding of how to compute them and get meaningful quantities out of this sort of device. Okay. How do we model spontaneous symmetry breaking here? We do exactly what we did in the case of the Ising model. We add a spontaneous symmetry breaking field. Remember now, if the symmetry is ON, then the spontaneous symmetry breaking field HB that I have written here will be an n component vector, and this will dot with this dot is in the internal components. It will dot with the field phi, and this is the Hamiltonian that we have to use for the broken symmetry problem. We have to compute this the partition function, this partition function with the symmetry breaking field, first take the thermodynamic limit and then set this HB going to 0, and that will give us the if the system for a set of parameters such as KTU have broken symmetry phase, then this device will pick out the correct probability distribution of the set of all possible over the set of all possible configurations. Okay. So that was something that we needed to add to our discussion. So we have completed that. So let us move on and let us think in terms of ground states and excitations of systems. Okay. So typically you will see that whenever you run temperature to 0, that is, you go to very low temperatures, typically you will see that some kind of symmetry is broken. That is quite typical. It is not necessary, but it is typical. And what happens is the system will pick out some kind of unique state, as we saw in the Ising model. So there is some unique state which we now just give a terminology for it. We will call it ground state. Even if it is classical, we will call it ground state. Typically the word ground state is used for quantum problems, but we will just extend that terminology to classical systems as well. So we can ask, there is a ground state which has the lowest energy, what are the excited states of the system? So why would we be interested in that? We would be interested in that because we want to study certain properties of these phases. That would be the reason, one reason why we would be interested in that. And the other reason is we will try to understand how, as you increase temperature, you will go to the symmetry non-broken state. So the excitations could become important in the process of making the transition from the symmetry broken to the symmetry non-broken state. Okay, let us start with the Ising model in a d cubic lattice with number of sides being L tilde. L tilde is a dimensionless side of the cube that you are putting this n sides in. So we will think of this as like a cubic lattice with all sides being equal. That is the simplest case. So the ground state for the Ising model, as we know, is the up polarized state when we have taken the symmetry breaking field to go to 0 in the positive, from the positive side. So this is what I call as the C up polarized state, right. And here all the spins are polarized up, and if I have n sites in the system in any dimension, you will see that the energy of this state is d, that is spatial dimension, times n number of sites times j, which is the exchange constant of the Ising model. So you can ask, what is the first excited state of the system? What is the state of the system that has the lowest energy above this ground state energy? So this is a state where there is a single spin flip, and the notation is it's all up polarized except the site j which has a down spin. That is the notation here. And so this is that state j, and this is the down spin. Okay. So what you find here is that the energy of the single spin flip state is equal to the energy of this fully polarized state plus, so this is the excitation energy, 2d times j. Why is it 2d times j? You can see that a certain number of bonds will be, links will be excited, and that is what gives you this. Okay. So the excitation energy now is given in this fashion, and what is interesting here is that you will see that this excitation energy is independent of the system size. So since it is independent of the system size, the excitation gap, there is a gap to excitation, and that is this finite number, and as I run the thermodynamic limit, this goes to a value of a finite value which is j dependent, and this is non-zero in the thermodynamic limit. And what we say here is that the Ising model has an excitation gap. So this is our main result here, that the Ising model has an excitation gap. So when I take the thermodynamic limit, the first excited state is a finite amount of energy above the ground state, and that finite amount of energy remains constant even if I take the thermodynamic limit. So we say that there is an excitation gap in the system. Okay, so that is what happens in ferromagnets. Now it will be also interesting for us to see what happens in antiferromagnets. So remember, if the exchange constant originally were positive, we would have had an antiferromagnet. So let us consider an antiferromagnetic Ising model on a d cubic lattice, and here again the number of sites goes as L tilde to the power d, and I have periodic boundary conditions, and C here is the set of all spin configurations, the set of all, a configuration of spins on the lattice, and that is denoted by C. So the Hamiltonian corresponding to the antiferromagnetic Ising model has J positive, but there is no negative sign here, so J positive. So what this will try to do is it will try to make spins on the nearest neighbors to point in opposite directions. Okay. So if you look at the ground state of the system, I have drawn the square lattice here. The square lattice has a very interesting property which becomes very useful in discussing antiferromagnets. What property does the square lattice have? The square lattice is what we call as bipartite. What do we mean by bipartite? Bipartite means that I will have the lattice sites can be grouped into two groups. They are called A sublattice sites, these are indicated by blue in this picture, and B sublattice sites. And the important thing is that if I look at the A sublattice sites, all their neighbors will be B sublattice sites, okay, and all neighbors of B sublattice site will be A sublattice sites. All the red sites have blue neighbors and all the blue sites have red neighbors. So this allows us to construct a ground state where, for example, I could put up spins on all the blue sites and down spins on all the red sites, and this state is called a nail state, and I have indicated as A up and B down. How do I get a configuration corresponding to this nail state, this C nail configuration? How do I get that from a symmetry breaking field? So now you will see that the symmetry breaking field that I will have is not the usual field which I had a constant field that I acted on all sides. So what happens is that the symmetry breaking field is called a staggered field. What do we mean by staggered? It acts as plus on the A sides and minus on the B sides. It acts in opposite directions. So it's as if that I have a plus field along A sides and minus field along B sides. So if I now do this calculation of first taking the thermodynamic limit and then letting the symmetry breaking field go to 0, in the way that I have discussed, if I take Hs is equal to positive and take it to 0, I will get this state as the ground state. Now you should notice something very interesting here. This state has not only broken the Z2 symmetry, it has also broken the translational symmetry, because you see this spin configuration is not translational invariant. If I translate this spin state, I will see that the A sublattives will get down spins and B sublattives will get up spins. Okay, so this state has also broken a lattice translational symmetry. So this breaks both the internal symmetry as well as the arena symmetry. Okay, so I invite you to ask what is the order parameter of the antiferromagnet. What happens if you do the opposite, namely HSB going to 0 minus? What is the excitation energy in the system, and is the system gapped? So this is a very interesting exercise. You might want to pause the video and work this out before you proceed. Okay. If you want a very interesting and challenging question, here is a very interesting statement here. I claim that the partition function of a system without any external magnetic fields, no symmetry break fields, nothing, the partition function in a d-cubic lattice of the ferromagnetic Ising model is equal to the partition function of an antiferromagnetic Ising model with the same magnitude of the coupling constant J. So this is a very interesting thing for you to work out. So I invite you to think about this. Okay. So now you see, energetically speaking, in the case of the Ising ferromagnet, there were just two states that had the lowest energy. One is fully up polarized and the other is fully down polarized in the absence of any symmetry breaking field, etc. Quite similarly, in the antiferromagnet, there is the nail state where there is A up, B down, and there is another kind of nail state where it is A down, B up. These are both flip related. So these two states are sort of the only two possible states with equal energy in the absence of any magnetic field. Now the question is, can there be systems where there can be many states with the same energy, all the lowest energy? So this is what happens in certain lattices, and it requires a phenomenon known as frustration. So we should now hunt for lattices which are not bipartite, that is, the sides of the lattice cannot be split into A and B so that A has only B neighbors and B has only A neighbors. So before you proceed, you can pause and you can try to think of what sort of lattices will give you non-bipartite structure in different dimensions. Well, I hope you found that the triangular lattice in two spatial dimensions is non-bipartite. Okay. So now if you try to find the ground state of the antiferromagnet, you will be little puzzled. So imagine I have an antiferromagnetic Ising model defined on the triangular lattice. So this is the triangular lattice that I am showing you here. So I can put a spin up here and the energy is minimized when this the spin on the neighboring site is down. So this link here, the one that I am pointing by this pointer here, is energetically at its minimum possible value. Okay. Now suppose I choose the spin to be up here, then this link will also be antiferromagnetically aligned. So one spin is up and other spin is down, so it is antiferromagnetically aligned. But this link here will have up, and therefore I will not be able to make this link satisfied. So this is what we mean by frustration. We cannot find something like a nail state as the ground state of the system. What is interesting is that there are many spin configurations which minimize energy. What is the energy minimizing configuration? Energy minimizing configuration is that every triangle has to have only one frustrated link. So for example, if I put a spin up here, this link will be the frustrated link of this triangle. So the claim is you can find many spin configurations in which every triangle has only one frustrated link. So let me show you that by a construction here. So I have taken the triangular lattice and I have found a hexagonal motif on the triangular lattice such as this. Okay. Now what I do, I start from the left corner here, put up spin, down spin, up spin, down spin, up spin, down spin. So you see all these links are unfrustrated. They have the ferromagnetic interaction, the energy is minimized because of this. Now here is the important thing. What do I do on the central site here, central to this hexagon? Now the point is you can put the spin to be up or down and it will produce a spin configuration. If I put up, there will be a spin configuration where all these 6 triangles which are making up this hexagon, there will be exactly one frustrated link in each of those triangles. Okay? This is very interesting. Now the remarkable thing is I can choose this to be up or down. That means there is two ways of choosing this and they will have the same energy. Now the remarkable thing is in every hexagon I can do this independently. It will still give me the same energy. So now you can see this very simple argument shows that there is a very large ground state degeneracy. There are many states. In fact, there are states which is exponential in the number of sites in the system. And what this does is, you know from elementary thermodynamics, elementary statistical mechanics I should say, that entropy is proportional to log number of possible states with the same energy. So what this leads to is what we call as ground state entropy. Okay. So here is a very interesting question for you to figure out. What would be an estimate of the ground state entropy per site for this kind of configurations of spins on the triangle, on the triangular lattice? This will of course give you a lower bound on entropy. There are many more possible spin configurations than what I am showing here. I am just illustrating the idea that there is a large number of states exponential in system size that are possible, and a very challenging question for you to work out would be to find out what is the exact ground state entropy per site. Okay, it is a very famous result, so if you find it, it will be your discovery also. Okay. Alright. So all these systems that I have discussed so far, they are gapped systems. That is, you have a ground state, it may be degenerate or it may have large degeneracy, but they are all gapped. So are there gapless systems, systems for which you can have excitations of arbitrarily small energy? Okay. So let me show you that that is possible. And what I am going to do is I am going to discuss for the first time an explicit model with a continuous internal symmetry. And the symmetry that I am going to consider is O2 symmetry. So, I am going to have a 2 component vector, and this model is also called as the XY model, in a 1-dimensional lattice, and 1-dimensional lattice with periodic boundary conditions is called a 1D chain. Okay? And so here is the model. So I have unit vectors sitting at every site, and those unit vectors can point in any direction. So this Ni is a vector at site I, and Ni, because it is a unit vector, can be thought of as cosine theta I minus and sine theta I. In other words, this n is characterized by an angle in some internal space. Remember, this angle is not related to some x axis and so on, right, because this is a 1-dimensional problem. So there is no y axis in space. So this degree of freedom is in some internal space, and J here is a coupling constant which is 0, and the interaction energy is that it is just the dot product of n here and n there, and if you just work this out from elementary geometry, you will see that this is just cosine of theta I plus 1 and minus theta I. So when I run the sum starting from I equal to 0, which is the first site here, it is a convention for numbering sites. You start with site equal to 0 and go all the way to n minus 1. So you will have n sites, and then the site I equal to n is same as the I equal to 1 0. This is why we call a 1D chain. It is as if it is an endless system. So it is like a chain. Okay. So periodic boundary conditions implies that I equal to n is same as is identified with I equal to 0. So what is the ground state of the system? So to formally calculate this, you have to put in a symmetry breaking field, which, remember, because it is 2 components, has to be a vector in this internal space. So I think of HB as with 1 along the along this first component and 0 along the other component. Okay, and this will give me a ground state where Ni are all vectors pointing in the sort of theta equal to 0 direction. So that is what is shown here, and what I have shown here is an example with n equal to 8. The system size is 8. So what are the excitations of this system? Okay, so you can definitely have gapped excitations. So for example, you can just take a configuration where the site at the middle of the chain. So if I have n sites here, the n by 2th site, that has this n pointing in the up direction. So instead of 1 0, it is 0 1, and you will see that this this will produce a finite amount of energy, which is actually 2j, and this will produce it is going to give you an excitation energy, and you can take thermodynamic limit and it will remain 2j, and therefore it is a gapped excitation. Now I want to show you that there are also gapless excitations. How do I show this? So imagine that I see, remember that this vectors n, they can sort of turn at to arbitrary angles. So what I do is I keep this where theta equal to 0, and then I turn this by a small amount, and I keep doing this such that when I reach the middle site, I am, say, going opposite to the going in the opposite direction, and then I undo this process and I bring it back here. Now you can estimate you can find out what is the sorry, there is an error here. This is going to pi, right? So this is a small mistake here. I'll correct this in the notes that we'll post, right? Okay. So you will see that you will get an energy, excitation energy, which is proportional to 1 by n. How do you get this? You see, the difference between any of these two will be proportional to pi by n, because as the change of angle going from one side to the next is proportional to pi divided by the number of sites. So the energy associated with this will be just cosine pi by n, and if I take n going to infinity, then I can do an expansion of this cosine, and this is how I get this energy, excess energy out. So you will see that the excitation energy is pi square by 2n times this j, and important and interesting thing, probably there is some small errors in the factor here which I will correct. You will see the important thing is that as n goes to infinity, you will see that this quantity goes to 0, which shows you that the excitation energy vanishes in the thermodynamic limit for such a twisting kind of excitation, and these are called spin wave excitations, and we have just demonstrated that they are gapless. So what we have seen is that you have systems which have gapped excitations, as well as there are systems with gapless excitations. It is important to understand that these gapless excitations will play crucial role in the physics later on that we will discover later on in the course, and they can give you very nice interesting phenomena particularly in lower dimensions. Okay, so we have now seen how to write Hamiltonians, how to model spontaneous symmetry breaking. We have learned how to characterize systems using order parameter. We have seen excitations and variety of associated ideas. Our next stop is to understand stimuli, how systems respond to stimuli. So we have gained a lot of understanding experimentally by probing systems, by acting some field on them, shining light, variety of stimuli we give, and we measure something experimentally, and we connect the stimuli and the response, and that connection is called a response function, characterizes the system. For example, again I will bring up this idea of the shear modulus which we discussed. If I apply a shear stress to a solid, there will be a shape change measured by a shear strain. So if you know how much shear stress you are applying, you can figure out by measuring the shear strain what is the shear modulus. So shear modulus is a response function of the system, or some response characteristic of the system. In the magnetic context, we can apply an external magnetic field, right, and remember this external magnetic field is a physical field that you are applying, and this should not be confused with the symmetry breaking field, which was a device that we used to do some calculation. Okay, mathematically look quite similar, but this is a physical field that you are applying in the laboratory. It will break the symmetry just like a symmetry breaking field, but it is actually a physical quantity that you are applying. And you may have done experiments that probe the magnetic properties of systems, and say you might have studied the Goy balance experiment in your BSc courses. Okay, in general, if you want to discuss responses, you can imagine the stimulus to be characterized by some kind of force. This is not literally the force like what shows up in Newton's law, it is what we just call a force that changes this, that tries to change the state of the system, and we find some kind of response R, and in general this response will be some function of this force, and generally this response will be some nonlinear function, and this R is called as some general nonlinear response function. Now what we are going to do is that we are going to posit, we are not going to prove, we can't prove this generally, we are going to posit, we are going to assume in a sense that systems of our interest have a linear response. What do we mean by that? What we mean by that is, if f is in some sense small, the response is proportional to f, right. In some sense this is the generalization of Hooke's law to any kind of stimulus and response. So the response we postulate is proportional to the stimulus, and the proportionality constant is some property of the system, some response property or some kind of modulus of the system. And as we saw in the case of the solid, such a response function can characterize the state of the system. And the key question we are asking is, how do we obtain this chi? Okay. So, we will first discuss the general theory of linear response, and then we will apply it to the models of our interest. So, a system with a set of configuration C and a Hamiltonian H, the equilibrium distribution at any temperature is given by this distribution function. And remember, when I write this, I have actually gone through the process of spontaneous symmetry breaking, etc., and it's just formally written down like this. Okay. What we are interested in is an observable A whose equilibrium value is obtained by taking the weighted average of the values in different configuration by the probability distribution given by this device. So, this is the equilibrium value. So, I have a system in equilibrium, and the expectation value of A, the observable A, is given by this non-script A, the usual Roman A here. Now, what I do is I stimulate the system by applying some kind of force. And what we are going to do is we are going to posit that this force will couple to the system via some observable B. Okay, I will make this clear in the next equation. So, that means the Hamiltonian of the system now changes to the original Hamiltonian that we had, right, this one, to F times B of C, where the energy of the configuration C with the forcing is H of C minus a convention F times BC. B is some observable to which this force couples. So, for example, if I have a solid and I try to apply a force, this force will couple to the displacement of the ions. So, this B will be something like a displacement. Okay. So, the partition function in the presence of this forcing field will depend on the Hamiltonian in the presence of forcing, and therefore, you will get this as the probability distribution over the space of configurations, where everything has an F subscript to remind us that we are now working with the force on. So, what is the response now? Since the probability distribution has changed from rho to rho f, I will get a new value of the expectation value of the operator A, and this is what I call as Roman AF, and the response is the difference of AF and A. So, AF is the one with the force turned on minus the value when there was no force, which is the equilibrium value. Okay. And the question we are going to pose is, how can I find a relationship between this delta A, which is the response, to linear order in F? Okay. So, what I am going to show you is a very special case of what in physics literature are called Kubo formulae, or they are also called Kubo-Greenwood formulae. We are going to look at a very simple version of them for static responses. Okay. So, let us do an explicit computation to compute delta A, and I will just walk you through the calculation. So, here I am going to use the notation that beta is 1 by temperature. Okay. So, start with AF. AF is, I am writing everything out explicitly. Here is the unnormalized probability e to the minus beta h, so this is just hf of C, and then I am putting in the value of AC to weighted average over the probability distribution. So, denominator has the partition function. Now, you see what I am going to do, I am going to expand the numerator to linear order in F. So, when I expand the numerator to linear order in F, I will get two terms. You can look at this term and you can see that the next term is this. How do I get that? I just expand, I see that e to the minus beta h c is e minus f bc is e to the minus beta hc multiplied by e to the minus beta fc and so on. And I will now put in this term here, and I will see I will get an expression like this. Okay. And now you will see that I can do the same thing for the denominator, and I will be able to go through the algebra and keep linear ordered terms, right, both in the numerator and denominator, and I will be able to then find that delta A is proportional to this quantity, which is 1 by T expectation value of AB now minus expectation value of A. So remember, that is just the expectation value of this operator times the expectation value of B, which is the Roman B. So it tells me now that delta A is proportional to F by this proportionality constant. Okay. And chi AB, which is the response function, is 1 by T delta A delta B. So what is this quantity delta A? Delta A is the fluctuation of A. So delta AC is AC minus the expectation value of A in equilibrium. So this is like a fluctuation. So what do I have here? I have fluctuation of A and fluctuation of B, and just a quick, you can check this yourself. The mean value of this fluctuation will be 0 because you've taken out the mean. So if you find the mean value of the fluctuation now, that will be 0. So what is this telling you? It is telling you that this response function for stimulating B, what is the response of the quantity A, is related to the correlation. So if I take two quantities and multiply them and find the expectation value, that is a measure, particularly the fluctuations. If I find the expectation values of the product of fluctuations, that is what we call as the correlations between the fluctuation of A and fluctuation of B. So Kubo formula gives you a very, very important result, that the responses of the system are determined by the equilibrium correlations of fluctuations. So I am taking a system and I am forcing the system by some force. There will be certain fluctuations in the system, and those fluctuations will be correlated. There will be fluctuations of A in equilibrium, there will be fluctuations of B in equilibrium. There will be a correlation between these fluctuations, and it is this correlation between these fluctuations that determines the response of the system to the external stimulus. This is a very remarkable result, and there are many generalizations of this, particularly if you put a time dependent field, etc., and it connects to something very important called as the fluctuation dissipation theorem, etc., which we will not discuss in this course, but it is something important to know, and you can maybe explore it in your free time. Okay, very good. So now let me continue and let me try to use this Kubo formula and try to find out some responses of something like the Ising model. So we will now use this Kubo formula to find the magnetic response of the Ising model. So what we are going to do again is we are going to say that the fluctuations are going to be computed in the configuration where we have already applied a symmetry breaking field, and then we have done the required thing to see whether symmetry is broken or not. So we will first apply a uniform magnetic field H, and again I want to emphasize that this H is a physical field that you are applying, it is not the symmetry breaking field. The symmetry breaking field has been applied and set, thermodynamic limit has been taken, everything has been set to 0, and this is now a physical field that you are applying. Okay. And so here is the Hamiltonian in presence of the physical field. So what we had called F in this context of the Ising model is now this external magnetic field, and it is coupling to n times the script m which we had discussed before. So this B of C is n times m of C. That is what so the idea is that the external field couples to the magnetization, that is the idea. And what is the observable A? Observable A is we are going to use the magnetization itself, because we want to see the magnetic response when a magnetic field is applied. Okay. So now you see the Kubo formula, the change of magnetization per site will be given by delta M, which will be chi, which is the magnetic susceptibility, times H, which is the magnetic field that you have applied. And this chi by our Kubo formula, remember the B is N times MC, so you get N, and then A is M itself, so it is delta A delta B, which in this context will be delta M times N delta M, N I have taken out, so it is just delta M square expectation value. So what you are supposed to do is you are just supposed to take this, use the density probability distribution that you have computed using the symmetry breaking field, etc., put it in this expression and compute the susceptibility, and that is the susceptibility that will compute. Okay, so let us go ahead with this computation. So first let us just recall all the formulae once again, so that we have everything ready in our hand. So chi, as we found in the previous slide, was N by T times the correlation of delta N and delta M, delta M and delta M. This M we had defined a few slides back is 1 by N times sum over all the spins in the configuration C. M, Roman M, is the expectation value of M. This is the magnetization per site that we have. Delta M is the fluctuation in the magnetization, and that is what we have put here, and you can easily calculate that this is what the formula for that is. So first let us look at the very high temperatures. Now when someone says high, you have to know high compared to what. So what I am talking about is temperature is much greater than the scale J, the exchange scale of the Ising model. Here we know and expect that the expectation value of the magnetization per site is 0. We know that we are in the paramagnet, and if you do not apply any magnetic field, spontaneously there is no magnetization, and the M is equal to 0, that is Roman M is 0. So this means that if I simply use this expression, delta M of C is same as M of C in the paramagnet, remember. Okay. So now we can see chi is N by T, the expectation value of M and M, and here we can do an explicit calculation by this substitution. So you will see that it is expectation value of Si and Sj. So you are now asking what is the expectation value of the spin I and spin j. But if you go very high temperature compared to j, then these spins are just fluctuating randomly. So there is no correlation between the spins unless they are the same spin, and then Si square will be 1, so the expectation value of 1 is 1. So that means the answer for this is delta Ij, which is the Kronecker delta symbol, that is expectation value of Si and Sj will be 1 if it is the same spin, otherwise it is 0 at high temperatures. And now I put all this together and I get a number. I find that chi is equal to 1 by T. Just pause the video and check whether you remember what this is. And if you found that the answer is Curie law, congratulations. So what we have done is all the hard work that we did has paid off, and we have recovered a well known result, which is that at very high temperatures a magnetic system will show Curie susceptibility, in that the susceptibility will be inverse in temperature. And so we have started from from microscopics, if you like, and derived a phenomenological result that we see in laboratory, in the sense that we have found the response function of a paramagnet starting from microscopics. So in some sense this is a very important calculation that we have done, a first non-trivial calculation, in the sense that we have got an answer which we can compare with experiment, and we know this works very nicely. Okay, let us look at the opposite limit. We can look at very low temperatures, and when you ask very low, you have to know relative to what scale. So that is T much less than J, So I would think of this as like T going to 0, it is like going to 0 temperature. And remember that we have computed that the probability distribution function is very simple there. The fully polarized up state is the only state that is there, all other states are thrown out because they are excited states, and there is an excitation gap, and therefore they will become improbable at any finite temperature. They will become improbable as temperature goes to 0. And the magnetization per site is m equal to 1. And now I invite you to do the calculation, and you will be able to show that as you go to 0 temperature, the susceptibility will vanish, the susceptibility will go to 0. Yeah, that is completely expected, because if I apply a magnetic field, all the spins are already polarized, so there will not be any change in the magnetization. This is the idea. Okay. Okay. Now you have to provide arguments, as I told you, to show that this is 0, so you should do this. Okay. Let me try to conclude this lecture, and before I do that, I will give you a few set of I will make a few more comments which will be useful as we go along. So this Kubo formula can be applied in very different contexts, and we can get various different kinds of responses. So for example, in the previous slide where we worked out the magnetic susceptibility, we applied a uniform magnetic field. But I could, for example, apply some magnetic field which varies on a lattice site to lattice site. So the magnetic field itself is a physical magnetic field which is site dependent. Okay. And now what I can do is I can define an expectation value of this spin, and let me call it mi. So this is the mean value of the spin in the equilibrium ensemble, and delta Si, which is the fluctuation, is Si minus this mean value. If I do this, then I will be able to see a very interesting result which you can easily work out, is that the change in this magnetization at that site mi, this change is related by a susceptibility which is space dependent, that is it will have I and j index on it, and this chi ij is 1 by t times again the fluctuation associated with this operator, the SI operator, and where am I applying the magnetic field, Hj, so that will be delta Sj, and that is what you will see. Okay. So now you see this rho infinity about which we are computing this, it knows everything about all broken symmetries, etc. Okay. And the important point is that this response function will carry all the information about any symmetry that is broken. Let me tell you what is the consequence of the broken symmetry in the context of response function of the ferromagnetic Ising model. The ferromagnetic Ising model, as we saw, does not break the translational symmetry. It only breaks the internal Ising symmetry. So now you will find that this chi ij that we have will depend only on the lattice vector connecting I and j. So for example, if I have two sites which are separated by by a lattice vector such as this, let us say, and I have two other sites which are separated by the same lattice vector but at a different position in the lattice, the chi ij corresponding to these two, this pair of sites and this pair of sites will be the same, because we haven't broken the translational symmetry. So symmetry of the state will also be imprinted in the response functions. Okay, so here is the question that I had for you. You can work out what is the susceptibility of the staggered magnetic field in the antiferromagnetic Ising model, and you can also work out some spatially dependent susceptibility in the antiferromagnetic Ising model and compare that with the ferromagnetic Ising model, and you can see the differences and how the symmetry difference of these two states will manifest in those response functions. Okay. So we have gone on for a bit in this lecture, so let me just summarize. We have looked at excitations and response. We started off the lecture by recalling things about fields in the continuum. We wrote down energy functionals and functional integrals. We will come back to this later in the course. We looked at gapped and gapless systems. We learned how to find the excitation gap of any system. We looked at frustrated systems and showed that they can have ground state entropy. This is very interesting from many perspectives. Of course, we will not have time to discuss that in this course, but it is something that you should be aware of, and these are areas that are of great interest. We looked at linear response theory, where we found out if we stimulate a system by some force, what will be the response. We worked out the Kubo formula, and the Kubo formula tells you something very physically appealing, which is that the response of a system is determined by the correlations of fluctuations in equilibrium. And we recovered, starting from the Ising model, a well known result, an elementary result that is taught to us very early in our science career, and this is the Curie law, and we started from microscopics and we derived it. So this is something that we can be very happy about. Okay, what is coming up next? So we have set up everything that we need to start actually trying to compute phase diagrams. Okay, and this is what we are going to do in the next chapter. We will compute our first phase diagram, or at least part of a phase diagram. So I am sure you will not miss the next lecture. So I will see you then. Thank you.